An object on a frictionless, inclined plane is assumed to undergo constant acceleration. In the absence of friction, there are two forces acting on the object. Gravity pulls straight down, and the normal force is exerted by the inclined plane perpendicular to its surface. Gravity may be resolved into two components, a component counteracting the normal force, and a component accelerating the object down the hill. If the plane makes an angle theta with respect to the horizontal, then the component of gravity pulling down the hill is mg sine theta. The expected acceleration is thus g sine theta. If the angle is 0, so the incline is flat, there is no acceleration. If the angle is 90 degrees, so the incline is a vertical cliff, the acceleration is g, the acceleration of gravity at the surface of the Earth. In this experiment, a cart will be rolling down an inclined track, and you will need to determine the sine of theta. Since the sine of an angle is defined as a ratio of the opposite side to the hypotenuse, we can measure the height of the lower edge of the track above the table at the 100 centimeter mark along the track. The height h is the opposite side, and the 100 centimeter length L is the hypotenuse. The ratio of h over L multiplied by g is approximately the acceleration of the cart. The presence of friction in the actual experiment ensures that the measured acceleration will be less than this ideal value. A word of warning: when you measure the height above the table, measure to the bottom of the track, since the apex of the right angle involves the intersection of the bottom edge of the track with the table. Remind the Data Studio software that there will be a motion sensor in use, and set the sample rate to 50 Hz. Use the sample options to set the stop time to 3 seconds. Be persnickety about the wheels on your cart so as to minimize friction. Release the cart from rest several centimeters below the motion sensor. Make sure the motion sensor is tilted in such a way as to follow the motion of the cart down the track. Begin collecting data as the cart is released. Construct graphs of position, velocity, and acceleration, all on the same horizontal time axis. Just drag and drop the Graph 1 icon onto each of the 3 measurements shown at the upper left. Remember that if you obtain flawed results, you can delete runs using the Experiment menu item. Notice that the position versus time is a curved quadratic shape, the velocity is a straight line, and the acceleration is a flat line for times when the cart is undergoing constant acceleration. Let's consider the acceleration versus time. Here we expect a flat line and wish to measure the mean value and the standard deviation to approximate the error. This mean value of acceleration may be compared with the frictionless prediction of g sine theta. Do you expect your actual measurement of acceleration to be greater than or less than the theoretical prediction of g sine theta? Click on the statistics icon. It looks like the Greek letter sigma, and check mean and standard deviation. It is very important to highlight the region of interest. You don't want the average to include any time before the release of the cart or time after it collides with the end stop. Now we will hold our data up for comparison with each of the 4 equations of accelerated motion in turn. Begin with the definition of acceleration, which may be written as final velocity v equals a times t plus initial velocity v0. There's a linear relationship between velocity and time, with the constant acceleration being the slope. Highlight the appropriate region of the velocity versus time graph and perform a linear fit. The slope of the straight line is a measure of the acceleration. Once again, you may compare with g sine theta. When there is acceleration, it's a horrible mistake to say that distance equals velocity times time, because the velocity is constantly changing. You may, however, use the average velocity times time to get distance, where the average is 1/2 the sum of the initial and final velocities. Again, highlight the straight line section of the velocity versus time data, the middle plot, and determine the mean value of velocity. Use the XY tool to determine the values of the initial and final velocities as well. Then average the initial and final velocity by adding them and dividing by 2. Is the mean velocity comparable to the average of the starting and ending values of velocity? In the position versus time graph above, stretch the XY tool like a rubber rectangle to span the same time values highlighted in yellow below. Find the time interval and the distance traveled. Check to see if the distance traveled is equal to the average velocity times the time. Position versus time is not expected to be a straight line. Rather, it is quadratic in time. That is, the distance the car travels depends on the square of the time. Instead of fitting a straight line to the data, we will perform a quadratic curve fit to a second-order polynomial. A comparison between the physics equation, position equals 1/2 at squared, with the mathematical quadratic form, y equals capital A times x squared, etc., shows that capital A from the model fit should be compared with 1/2 the acceleration. Again, highlight a region in the upper graph of position versus time and perform a curve fit to a quadratic function. Record capital A and compare with 1/2 times the acceleration. The fourth equation of accelerated motion states that v squared equals 2a delta x plus v initial squared. Thus, a plot of v squared versus position, delta x, is expected to be a straight line with a slope of 2 times a. The Calculate menu button at the top center of the Data Studio screen enables us to create a variable v squared. Define the function v squared equals x squared. Then click where it says to please define the variable x and choose Data Measurement. Select the velocity data and it will compute the square of velocity. Drag and drop a graph onto this newly defined variable v squared and then click on the title along the x-axis to change it from time to position. Now you have v squared versus position, which is expected to be a straight line. Ignore the data at the lower right, which represents data after the bounce off the end stop. Highlight the straight line portion and fit a straight line. The slope is to be compared with twice the acceleration. With constant acceleration, the position versus time graph is constantly curving as the velocity increases. The instantaneous velocity is just the slope of the tangent to the curve at any instant of time. Experimentally, we can compare the slope of the tangent line at some moment of time with the corresponding value of velocity at the same time in the velocity versus time straight line graph below. In the topmost graph of position versus time, highlight 3 adjacent points and perform a linear fit to approximate the tangent at that moment of time. Drop to the middle graph of velocity versus time and use the XY tool to measure the velocity at the same time. Compare the slope of the tangent to the curve with the instantaneous value of velocity.